adopt this approach of ordering-based semantics. What is this all about? Well, instead of taking the actual values, we're only interested in the rankings. And the rankings are actually quite robust in terms of the values. So if you look at the decision boundaries, there is no need for the decision boundaries to agree in order to ensure that the rankings agree. So in terms of the linguistic theory, you have speaker and hero. You give speaker the city X, and X has 123,729 population. So to what degree is X a small city? So you ask two people, and they will give you a different degree. That's almost for sure. But you ask both of these people to rank a number of cities according to the degree to which they are small cities. Then you will most likely get the same ranking. So those rankings are pretty robust. So we see that for these two characteristic functions, the decision boundaries don't coincide, but at the same time, the rankings do coincide, because whenever there is a value that's smaller here than another value, then it's also the case for the other function. Okay, my talk has been going on for 30 minutes, which is why I will now give you a Dilbert episode. Okay, do I have your attention again? We will come to questions later. So let me just give you a summary once again. We're doing a natural language database interface. What we want to do is we have a natural language expression. We're interested in all hot, dry cities. And then I came up with this prototype, and that actually ranks all the records in our database according to the degree to which those records fulfill our intuition about something being a hot, dry city. So we get records with high rankings that have high temperatures and low number of wet days, and then you get the right rankings. This is possible by saying that there is a natural correspondence between the way we define a data model, the sort of objects we have in a data model, like tables, and lexical types like nouns. So you use a noun like city to refer to a record in a place table. You use an adjective like small or big to refer to a certain range of values in a certain attribute. And this is done by actually specifying a linguistic data model in a linguistic data modeling language that I've come up with. So this will plug some linguistic information into a grammar, and then our natural language database interface can use that grammar to take any expression like hot, dry city, plug it into the linguistic knowledge base, get back a logical form, plug that logical form into an SQL statement, run that statement against the database, and return the data to the user. And now comes the philosophical part of the talk, which is we will talk about fuzzy logic as a generalization of bivalent logic. And looking at these logical things, it really, for me, this was a great eye-opener about the way logic in general works, and about what sort of models you can actually build with logic. So in fuzzy logic, we need a conjunction operator that actually was involved in our SQL statements. And the way a conjunction is defined in fuzzy logic is to say that any operation on the unit interval can be a fuzzy conjunction as long as it's commutative, associative, just like a normal conjunction, as long as it's non-decreasing and has one as a neutral element. So those two basically boil down to saying that a conjunction can never be any truer than any of its conjuncts. And actually, psychologically, this is a sort of interesting question, because psychologists have been looking at what they call the conjunction fallacy for quite some time now. So what a psychologist will do to find out intuitively what people are doing when they're trying to come up with conjunctions is they give people, for example, a story about Mary. And then they ask them, is Mary a secretary? Is Mary likely to be a rich secretary or something? And then you get people thinking that it's more likely that Mary is a rich secretary then that Mary is a secretary. So in terms of probabilities, of course, this mathematically doesn't really work out, but there is a very interesting field to this in psychology in trying to find out how people deal with logic intuitively, as opposed to the way we do it in mathematics, where we just come up with a couple of with a couple of definitions. So, but nevertheless, for fuzzy logic, this is the way a conjunction is defined, and it tends to work out pretty well, and it tends to correspond to what humans do not too badly. Although the psychological elements, again, this is something that is very different here from the 70s approach to artificial intelligence. Because in the 70s, people said, we can simulate what a human brain does, we can have a computer do anything that a human can do. But simulating what a brain does in a computer is actually something that no one really believes can be done nowadays. So in the 70s, this was the approach. Nowadays, this isn't the approach. So we kind of just took the engineering approach, made a couple of definitions, and see whether it works out. So the standard triangular norms that are often used in fuzzy logic is you do a minimum, for example. So you have proposition P, which is true to degree 0.8. Q is true to degree 0.5. And then the conjunction P and Q is true to degree 0.5 if you use the minimum, because that's the smaller value. Or you could do a numeric product, so that would make it true to degree 0.4. You can do this Lukasiewicz T-norm, or you can use a drastic product. So those are all sorts of definitions that you can do. This is more or less the standard definition, which is to say that the conjunction is defined by minimum, and the negation is defined by this standard negation that says that P is true to degree 0.8, then not P is true to degree 0.2. And then, of course, if you have an AND operator and a NOT operator, that will give you a full logic. And this logic is called a Gödel logic in that case. Or you can use products here, then you get a product logic or Lukasiewicz logic or whatever. So the cool thing about logic is that it underlies pretty much anything. But for computational theories, it gives you nice generalizations over what's going on. So think about a finite state automaton. You have a number of states that are interconnected, and you can make a transition from one state to the other state. And then any state can accept a certain number of symbols or not accept them. So then you say that a certain string is in the language defined by that automaton. If it fulfills the requirement that the first state accepts the first symbol, and you make this transition, and the second state accepts this symbol, and you make this transition, or you make this transition, and the second state accepts this symbol and the second. So this whole thing is just a big disjunction of conjunctions. It's just a disjunctive normal form. So usually this is done using a normal bivalent logic, of course, which is sort of boring. So by using fuzzy logic, you can stick any triangular conorm here and any triangular norm here. And of course, doing this thing with the regular automaton and having numbers between 0 and 1 is actually kind of familiar, because we do that with Markov models. All of you who have ever heard of Markov models will probably have seen this this statement before, where we plug a product here and a sum here, and we compute the likelihood of our Markov model accepting a certain expression in the language. So this likelihood can be determined using a forward algorithm, and this forward algorithm will actually compute exactly the value of this statement. So it will compute the product here and the sum here. And we can also do a Viterbi approximation here, which is a bit faster. So and that will put a maximum here instead of a sum. But now we see that the sum and the maximum are actually just two different triangular conorms, and the product is just a triangular norm. So you can actually put any sort of logical statement here and see if this works. So basically this fuzzy logic stuff gives you a nice generalization over pretty much all of computational theory and not just the linguistic stuff, which is sort of neat. But for the language modeling problem in particular, again, you can actually induce fuzzy context-free grammars from corpora. So remember the talk yesterday by Dan Kaminsky? He trained this context-free grammar on a certain file to see what's actually going on in the file and to find out about what the syntax of this file is and what the protocol looks like and stuff like that. So he does that using normal context-free grammars. And using fuzzy context-free grammars, you can actually do the same stuff but have a sort of degree of match between symbols and stuff like that. So it's a nice generalization of a normal context-free grammars. But for really working out syntax, there isn't too much point in using fuzzy logic. What fuzzy logic is really cut out to do is doing semantics. Because in semantics, you could say that, well, this sort of seems like probability theory to me, isn't it? You have these values between 0 and 1, and you want to have a conjunction, then you multiply them and stuff like that. Isn't that probability theory? Well, actually, no, it's not. Because if you're looking at BALD, and you say that BALD of x is a probability density function, then what probability theory is all about is dealing with uncertainty. And uncertainty is mathematically very different from vagueness. Because if you have perfect certainty, if you know that there are exactly 76,273 hair on a person's head, and you want to ask the question whether that person is bald, and you plug that value into a probability density function, well, then the probability will be 0. You will maybe never have observed a person with exactly that many hair, and therefore, probabilistically, you can't say whether that person is bald or not. So what's, of course, done in probability theory is that you define confidence intervals and look at probabilities of something to lie in a confidence interval and stuff like that. But it doesn't really make sense for fuzzy semantics because how would you define those confidence intervals? And the other thing is that in probability theory, you need an independence assumption for a conjunction. So you flip a coin, the probability that it turns up heads is exactly 0.5. You flip a coin twice, the probability that it comes up heads twice is 0.5 times 0.5. Doesn't that look like a fuzzy conjunction? Well, no, because a conjunction is something logic, whereas a probability looks at event spaces. So that means that if the first event of throwing the coin for the first time and then the second event of throwing the same coin for the second time are completely independent, then you can do the conjunction, the probability of the co-occurrence actually by working out the product, but you can't do that if the events are correlated in some way. And actually doing logic on events means that you're already assuming that there is some sort of relationship between them. And that means that it doesn't really make sense to make an independence assumption here. So what's different between probability theory and fuzzy logic is that fuzzy logic is a logic in the sense that it has a truth functionality. The degree of fulfillment of a statement which is composed of other smaller statements is a function of the truth values of those smaller statements. Whereas in probability theory, it's not a function, the probability of, say, a co-occurrence is not a function of the probabilities of the occurrences of the events, but it's a function of what's actually going on. You actually have to look at the events and whether they are independent and justify those assumptions. And those assumptions tend to be really hard to justify for doing linguistic stuff. So this is the theoretic part of the talk, which then concludes the whole thing. And at this point, I want to remind you once again that why I'm standing here is because I really want to inspire some of you guys to go away and maybe do some technology transfer and maybe employ this kind of stuff in a useful way. So if at any time during this talk you've said to yourself, wow, this sounds like fun, I can think of a cool application where I can plug this stuff in, then please do feel free to come and see me afterwards, and I'll be happy to collaborate with any of you on on cool projects involving this kind of stuff. So at this point, I say thanks for your attention, and